Okay, let's start gradually. Okay. Okay. So we are going to talk about the Fourier transform for ordinary functions, and then Fourier transform for distributions. Okay, when I say ordinary function, not every ordinary function, for a particular class of ordinary function, and then the Fourier transform of distributions. So we have today, this week, and next week, yes, we can finish up everything. Then we will be ready for, sorry, for midterm exam. It means the next week will be our last week or last meeting before midterm. Okay, if you are ready, let's start. Fourier transform. Look at here, I mentioned something that for the discussion on the Fourier transform, we only focus on one-dimensional space R, okay? But what we are going to discuss is valid or true for n-dimensional space Rn, but we just only focus on R. But bear in mind that the discussion that you are going to see is valid for Rn also. Okay. Fourier transform and its inverse. Definition and basic properties. Okay, you make a note of this first. So it means in general, we can talk about the Fourier transform on Rn or n-dimensional Fourier transform. But we only, to make it simpler for you, we focus on R. Okay. Fourier transform and its inverse, basic properties. Okay, we have a definition here. A function like f from R into C, it means a complex value function R, is called absolutely integrable, okay, absolutely integrable if, look at here, the integral of modulus or absolute value of fx dx on R, which means this improper integral from minus infinity to infinity. The absolute value of fx dx, when I say less than infinity, this one maybe mathematically is not correct. This means this integral is conversion, okay? So a function like this is called absolutely integrable if the integral of f on R, which is actually an improper integral, is conversion, okay? So please make a note. You are going to see that for this kind of function, we are going to define Fourier transform. I have prepared some example of absolutely integrable function here for you. Like you can see the first example. It is easy. I'm gonna leave it to you to check. Okay, here. Function fx defined by, on R, okay, on R, defined by, for every x in this interval, x otherwise 0, okay? This is an example of an absolutely integrable function, okay? This is easy. I'm gonna leave it to you to check that the integral of f on R is conversion, okay? It is easy. Another example that I have prepared for you It's this one. The function gx. Okay, purposely I provided this example to be complex valued. Function gx given by I divided by 1 plus x squared. Okay, this is another example of an absolutely integrable function. Okay, I'm gonna show this for you. This is easy. I leave it to you, but I'm gonna show this for you. It's also not so difficult to see. So F, G are two, and one more actually here. I provided one more. You make a note first of all examples, then I'm going to show you that Gx is absolutely integrable. Another example here is this I've provided. Look at here, this function, h of x. For every x between 0 and pi, greater than 0, less than pi, sine x, otherwise 0, okay? This is another example of an absolutely integrable function, okay? H and F are easy to see, okay? I'm gonna leave it to you. It's just like simple calculus. G also, but I would like to discuss G for you, sorry. So please make a note first. So Hx for every x between 0 and pi, sine x, otherwise 0. This is also an example of an absolutely integrable function. And bear in mind, look at the definition of absolutely integrable function. The function might be complex valued. Yeah, of course, in general, we define it for complex value. But when you take absolute value, so this integral and this function totally will be real value. Absolute value of fx is a real valued function. So, okay. Okay, F, G, and H. Okay, now let me show you that G is an absolutely integrable function here. Okay, let's move here to our board. So we're gonna calculate this. So let's calculate the integral from minus infinity to infinity, the absolute value of gx dx. Okay, and look at here. You agree with me? This means I can write this one integral from minus infinity to 0, absolute value of gx the absolute value of gx dx plus integral from 0 to infinity, right? The absolute value of gx dx, correct? And look at here, when you say integral from minus infinity to 0, actually means limit, right? Limit, like integral from a to 0. Here a approaches minus infinity. And here we have, okay, let's put the formula of G. G is I over 1 plus x squared dx, correct? Plus here. And this integral, when you say integral from minus 0 to infinity, it means integral from 0 to like b approaches infinity. Absolute value of I divided by 1 plus x squared dx. Correct? So let's move on here. So we have limit a approaches minus infinity, integral from a to 0. Look at here, absolute value of I is 1, and the absolute value of 1 plus x squared is always positive. So we get this simply 1 over 1 plus x squared dx plus limit b approaches infinity, integral from 0 to b. This one also, the absolute value of same. The absolute value of I is 1, and the absolute value of 1 plus x squared equals itself because it is always positive, dx. Okay. I think we can erase here to have some more space. Okay. That should be easy, right? Now, what is the antiderivative for this 1 over 1 plus x squared? Do you remember? It's just calculus. Huh? Okay. If you remember, the integral or antiderivative for this function is tangent inverse, right? 1 over 1 plus x squared is the derivative of tangent inverse, right? So for the first one, we have here limit a approaches minus infinity. Okay, tangent inverse, right? Tangent inverse x, it means arctangent from a to 0, right? Plus similarly, limit b approaches infinity. Okay, the antiderivative for this function, tangent inverse x from 0 to b. Okay. Let me erase the middle line. I believe that we don't need it. Okay. We are almost there, right? You can calculate. What is the answer? Actually, okay. So we have limit here. Limit a approaches minus infinity. Okay, here we have tangent inverse 0, okay, minus tangent inverse A, okay, plus limit B approaches infinity, tangent inverse B minus tangent inverse 0. Tangent inverse 0. Okay. Now what is the answer? Tangent inverse 0 is 0, right? And what is the limit of tangent inverse when A approaches infinity minus infinity? Do you remember? This is when A approaches minus infinity, the limit of tangent inverse becomes minus pi over 2, right? And the limit of tangent inverse when B approaches infinity becomes pi over 2, right? Okay. So you can see that this integral is convergent. Okay. So here, so tangent inverse 0 is 0, right? Okay. Minus, when A approaches minus infinity, the limit of tangent inverse is minus pi over 2, right? Do you remember? Okay. Plus here, the limit of tangent inverse B when B approaches infinity is pi over 2, correct? It's pi over 2. And the limit of tangent inverse 0 is 0 because it's constant. Okay. So if you calculate becomes, look at here, pi over 2 plus pi over 2, the answer is pi over 2 plus pi over 2. And the answer is pi. This means convergence. So you can see the integral of absolute value gx dx is convergent. So this means that g is an absolutely integrable function. So we show that, right? Okay. Okay. So these are some examples of absolutely integrable functions. Next, look at here. A set of all absolutely integrable functions, okay, is denoted by L1R. You read it L1R, okay? And It means this actually, L1 of R or L1R is defined to be, look at here, the set of all functions from R into C. It means complex valued functions on R such that this integral is conversion. And when this integral is conversion, it means f is an absolutely integrable function. So it means the set of all absolutely integrable functions is denoted by L1 of R, okay? And be very careful here. This is a very well-known fact, okay, in functional analysis, that L1 of R is a Banach space with L1 norm. L1 norm is denoted by this. Look at the norm sub 1. And this L1 norm is given by this. It means when you have an L1 function, you have some, sorry, when you have an L1 function here, like f, this integral is conversion, right? And look at here, since you take the integral of some non-negative function, so this integral is some non-negative value. So if we define, if corresponding to f, we consider this value, which is non-negative value, this defines a norm on f, okay? And defines a norm for f, which is denoted by norm 1. So the norm 1 f, the norm, L1 norm, sorry, L1 norm of f is defined to be the integral of the absolute value of f on R, okay? Without proof, please accept it without proof, but that this L1 of R is a Banach space, okay? This is a very well-known fact in functional analysis. But I'm not going to prove it for you, and I will not ask for it. Just know that this L1 of R, which means the set of all absolutely integrable functions. Okay, first of all, is a vector space with pointwise operations. So it's a vector space. It has a norm, L1 norm, okay? So along with this norm is a norm space, but actually it's complete. So it's a Banach space, okay? So L1 of R with this L1 norm is a complete norm space. So it's a Banach space, okay? Remember, bear in mind. And sometimes when f belongs to L1 of R, we say that f is an L1 function, okay? So bear in mind, L1 of R is the vector space, actually, of all absolutely integrable functions. When we say vector space, it means with pointwise operations, okay? And actually, it's a norm space with L1 norm, and it's complete with this norm. It's a complete norm space. So it's a Banach space. Next in remark, we are going to introduce some more spaces here that we need. Okay. Look at here next. CCR, okay, denotes the set of all continuous complex valued functions with compact support, okay? It means when we say CCR, okay, basically, is a set of all functions from R into C which are continuous with compact support, okay? Which are continuous with compact support. So CCR, it means the set of all complex valued continuous functions with compact support, okay? Actually, it's a vector space, and actually it has a norm, okay? And actually it's a Banach space also, but okay. You just know that it is a vector space. For example, this function h of x given by this sine x when x between 0 and pi, sine x otherwise 0. This is an example of a function here. It means this function h of x is a continuous function with compact support. I leave it to you to check, but quickly I can explain this one. I mean, you can see by the graph of h, this is like continuous with compact support. If I'm not mistaken, last time when we were talking about the definition of a support of a function, we calculate. Okay, but just quickly here, let me show you. Go back here, just quickly by graph. Something like this. Roughly, the graph of this function is like this, right? Let me check again. Yes, between 0 and pi sine x. Otherwise 0, it means the graph of this function is like this. Something like this. Roughly, okay. Something like this. So here is 0, here is pi. Actually, here is pi over 2, and here is 1. Okay. So at this pi graph, you can see there is a continuous function. Look at here. Here we say between 0 and pi, okay? But if you take limit, left-hand side, right-hand side limit at 0 and pi equals the value of the function at 0 and pi, which is 0. So this function is continuous, actually. It's continuous, and what is the support of h? Huh? What is the support of h? Do you remember the definition of support? Okay, the support of h is this. The closed interval 0 and pi. And as a subset of R, okay, as a subset of R, since it is bounded and closed, it's compact, okay, by Heine-Borel theorem. So you can, by Heine-Borel theorem, there is a closed and bounded subset of R, so it is compact. So you can see there's a continuous function with compact support, okay. So H belongs to CCR, okay. So H is a continuous function with compact support. The support of H is this, a closed interval 0 and pi. And look at, okay, yeah. For example, this function H belongs to CCR, but here we have some interesting and important fact. Moreover, we have CCR is a subset of L1 of R. It means the space of all continuous function, complex valued, okay, with compact support is a subset of L1 of R. Huh? And actually, more precisely, okay, I just mentioned this, you accept it without proof, that actually CCR is dense in L1 of R with L1 norm. It means the closure of CCR with respect to L1 norm becomes L1 of R. Okay. You accept this without proof, okay, but at least you should be able to answer this. Why do we have CCR a subset of L1 of R? Huh? Do you have any idea? So you make a note first, then I'm going to quickly explain. Actually, this is quite easy to see that why CCR is a subset of L1 of R. Why every continuous function with compact support is an L1 function, is an absolutely integrable function. Why is it like that? Okay. You make a note of this. I'm going to explain it. So look at here. As I mentioned, actually, this CCR is a vector subspace of L1 of R. So like it can borrow the norm, L1 norm from L1 of R. So actually, CCR, okay, with L1 norm is also a norm space, okay, but it's not complete. But the completion, it means if we take closure, will be L1 of R, okay. Okay, let me explain you here. Okay, so we are going to show this, okay, that CCR, okay, CCR is a subset of L1 of R. This one we want to show. So you suppose that F belongs to CCR, okay? So what does it mean? It means F from R into C is a continuous function with compact support. And now if we try to calculate this integral, look at here, the integral from minus infinity to infinity, the absolute value of fx dx. Look at here, the function f is compactly supported, right? It means outside a compact set, it is 0. So this integral equals, look at here, this integral equals the integral of the absolute value of f, you tell me, on k. K is the support of f, is a compact set, okay, dx. K is the support of f, which is a compact set, okay? So it means we get this. And let me continue here. We get integral absolute value of f x dx on k. K is a compact subset of R, which is the support of f. Now look at here. F is continuous, right? The absolute value of f is also continuous function on compact set. Okay, so continuous function maps compact to compact. So it means actually this function on compact set k is bounded. Okay, so definitely this integral will be conversion, like will be something like this, less than integral m dx. M is the upper bound of f on k, something like this. And this equals m integral dx on k. And this definitely finite, like conversion, okay? Because this is the Lebesgue measure of k actually. So you can see that if f is belongs to CCR, it means a continuous function with compact support, then the integral of absolute value of f on R is conversion. So what does it mean this? It means f is absolutely integrable, right? F is absolutely integrable. It means f belongs to L1 of R, correct? So we prove that this is a subset of L1 of R. And not only that, we can say like this, the closure, look at here, the closure of CCR, okay? The closure of CCR will be L1 of R. But remember, this closure is being taken with respect to L1 norm, okay? Usually they write it like this. Let me write it here. Usually they write it like this. Usually they write it like this. Okay, they say like the closure, they put it like this to emphasize that this closure is being taken with respect to L1 norm. Okay, is L1 of R. It means this CCR is dense in L1 of R with respect to L1 norm. So this closure is with respect to L1 norm. Okay. So this is interesting. It means if you take like any L1 function, okay, then you can have a sequence of compactly supported function continuous, which is conversion to that one. And if I want to, explain this one like with some graph, roughly like this. Let me erase here. So this discussion shows that CCR is a subset of L1 of R. Like for example, if we have a function like this, for example, something like this. If you have a function like something like this, kind of a step function, you can imagine that here empty, something like this. Okay, the rest 0. For example, this is definitely a kind of L1 function. This L1 function can be approximated by some or a sequence of CCR functions, something like this. Look at here, if I consider a function like this. Okay, roughly speaking by graph, something like this. This is some L1 function, but can be approximated by some CCR function. This is a CCR function, a continuous function with compact support, something like this. Like we can have better approximation. This is another one, which is like roughly better approximation, something like this. Okay. Okay. Now, listen very carefully. The definition of Fourier transform for a L1 function. The Fourier transform of a function in L1 space, okay? It means the Fourier transform of an absolutely integrable function like f is denoted by f hat. You read it f hat or f of f. This means the Fourier transform of f. And defined by, look at here, and defined by this. So look at here. If f is an absolutely integrable function, the Fourier transform of f, which is denoted by f hat or f of f, is also a function. It's also a function. And the value of this function at every omega, this is actually not w, omega, okay? You may use any notation, it doesn't matter. F hat at omega is given by this. Look at here, 1 over the square root of 2 pi integral of ft exponential minus I omega t dt. Okay, let me make it bigger for you to make a note. Yes. So f hat, the Fourier transform of f, which is a function, I'm going to mention shortly later. It's kind of particular continuous function actually. F hat at omega is given by this. It means the value of the f hat at every omega is given by 1 over the square root of 2 pi integral of f of t exponential minus I omega t dt. Okay. So you can see for this integral, t is variable, but omega is a constant. Okay. So this is the definition of a Fourier transform of an L1 function or an absolutely integrable function f. For every omega in R. It means f hat is also a function from R into C. The Fourier transform of f is a function like f hat from R into C given by this or defined by this. And okay, just know that this is a well-known fact in function analysis that the Fourier transform of f hat, which is a function, is kind of a specific function, belongs to a specific space of continuous function. Actually, f hat belongs to the space of C0R. C0R, it means the space of continuous function which vanish at infinity. Okay, but we don't need to go through the details more. You just know that if f hat the particular or specific kind of function, continuous function. Okay, so you just know that f hat is also a continuous function. Okay, f hat is a continuous function actually. F may not be, f is an L1 of R. Okay, f may not be continuous. Okay, but f hat, the Fourier transform of f is continuous, a kind of a specific continuous function. Actually, the Fourier transform of f belongs to a space of continuous functions which vanish at infinity, denoted by C0R. Okay, but you don't need to know that much. Okay, just know that f hat is a continuous function. F is an absolutely integrable function. Bear in mind, f may not be continuous. Okay, just like this. Look at here, this is an L1 function, absolutely integrable function. It's not continuous, fine. So f may not be continuous, fine, but f hat, the Fourier transform of f is definitely continuous. So be very careful. that an absolutely integrable function is not necessarily continuous, okay? This one. When we say f belongs to L1 of R, it means just that integral is convergent. So when we have some absolutely integrable function may not be continuous, but the Fourier transform of f is definitely continuous. So be very careful. Okay, next we are going to see some interesting example in which we are going to compute the Fourier transform of some absolutely integrable function here. Okay, you can see. We are given this absolutely integrable function fx for every x between, and you can see this f is not continuous, okay? This f is not continuous. An absolutely integrable function is not necessarily continuous, bear in mind. So you already, okay, if you remember, we mentioned about this example earlier that this is an L1 function. This is an absolutely integrable function. Okay, this is easy to see. What we need to do here is to compute the Fourier transform of f. Okay, so you make a note, we are going to do this. We want to find the Fourier transform of this absolutely integrable function. Okay, so let's do it. Let's move here. Okay. We want to calculate the Fourier transform of this function, right? The Fourier transform of this function. Okay. So the Fourier transform of f, which is denoted by f hat at omega. Okay. So you recall the formula. Okay. F hat of omega equals 1 over the root of 2 pi integral from minus infinity to infinity, it means on R. F of t or f of x, it doesn't matter. That's just notation. Exponential minus I omega t. Okay, this is omega actually. Okay, maybe it looks like W, but it doesn't matter. It's just notation. dt. Okay, look at the definition here. ft exponential minus I omega t dt. Okay. But look at here, look at the formula of f. Okay, you can see outside interval minus 1 and 1, the function is 0. So this integral will be reduced to 1 over the root of 2 pi. So here we said from minus infinity to infinity, but it is only left from, look at here, from minus 1 to 1, because outside this interval the function is 0 actually. So this equals integral from minus 1 to 1 f of t exponential minus I omega t dt. Let's move here, and this equals 1 over the root of 2 pi integral from minus 1 to 1. And look at here, in this interval, what is the value of f from minus 1 to 1? In this interval, the value of f is 1, right? So ft equals 1 here. So put 1 here. So you only have exponential minus I omega t dt. Okay. And for this integral, look at here, minus I omega is constant. Okay, t is variable. So this equals 1 over the root of 2 pi. Okay, now somebody tell me, what is the integral of exponential minus I omega t dt? This minus I omega is like scalar constant, like alpha. So what is the answer to this integral, the antiderivative for this? So do you agree with me? This equals 1 over minus I omega exponential minus I omega t from minus 1 to 1, correct or not? Like if you use substitution, if you take this minus I omega t to be u, okay, if you use substitution, you get this, right? Definitely the derivative of this function is this, right? The derivative of the exponent is minus I omega, will be simplified by this times itself, correct or not? So just calculate, should be easy for you. So this equals, okay. And here, let's simplify something here. If I multiply numerator and denominator by I, okay? If I multiply this one by I, and here by I, here we have I, and okay, can we simplify this one? If I multiply this one by I, okay. Do we need to do this? Okay, if I multiply this one by I, this one I, so I squared is minus 1 minus 1, okay. Maybe we can do like this. So I can write it as, yes, look at here. If we multiply numerator and denominator here by I, so here we have I, here we have I minus I squared, but I squared is minus 1 times minus 1 become 1. Okay, so we have this actually. I over the root of 2 pi. We just do this for simplicity, okay. 1 over omega. Okay. So this is about this, okay, 1 over omega and 1 over minus I equals I actually. And the value of this function when t is 1 minus, when t is minus 1. So we have exponential minus I omega minus exponential when t is 1, okay, when t is minus 1, this becomes I omega. Okay. Now, what is next? Do we have any idea what should we do this with this? We have to use what they call it, we have a well-known, what they call it, Euler, right? Euler formula. If I'm not mistaken, they call it Euler. Okay, it means like we are going to use this. Okay. Now, okay, we are not done yet. We have to simplify this as much as possible. Okay, this one. Okay. Now, to simplify this, we are going to use this formula. If I'm not mistaken, they call it Euler. We are going to use it. Do you remember, we know that we have exponential I theta, okay, for every theta equals cosine theta plus I sine theta. To simplify this, we are going to use this formula. If I'm not mistaken, it's called Euler formula, something like this. We are going to use this, okay? Okay. So it means, okay, so it means here, okay, exponential I omega equals cosine, okay. So exponential I omega equals cosine omega plus I sine omega. And exponential minus I omega, okay, which means I minus omega equals cosine minus omega, which is equal cosine omega, okay, plus I sine minus omega, which is minus I sine omega. Okay, now look at here. We have exponential minus I omega minus this. So what do you get here? What do you get here? Okay, this minus this. Okay. Now you calculate this and put it here. Okay. Let's go to a new page. I need to, let me save here. So look at here, exponential minus I omega equals this, exponential I omega equals this. So now this minus this becomes minus 2I sine omega actually. Okay. So let me save this page. Okay. 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 So let's continue the calculation in the new page using this. So we have I over the root of 2 pi 1 over omega. Okay, look at here. Now if you calculate, exponential minus I omega is this, minus exponential I omega. So this minus this. Cosine is gone, so we have minus I sine omega. So become minus 2I sine omega. Okay, this is easy to calculate. this minus this. Cosine omega is gone, so we have minus I sine omega minus sine. Okay, so this minus this becomes minus 2 I sine omega. Okay, like this. So now let's calculate. Look at here. Minus I times I. Okay, so we look at here. I times I squared is minus 1. Times this become plus. So we get this actually. 2, okay, 2 divided by the root of 2 pi uh, 2 divided by the root of 2 pi sine omega divided by omega. Okay. Okay, correct or not? Yes, I squared is minus 1 times this plus 2 over the, okay. And let's simplify this. Look at here. This 2 means the square root of 2 square, right? So if you simplify it, actually you get this. The root of 2 over pi, actually you get this. Okay. Sine omega divided by omega. But be very careful. Something that I should have mentioned from the beginning is, look at here. Here, omega must be non-zero for this calculation, okay? Something that I should have mentioned earlier, but it's fine. It means, look at here, f hat is a function of omega. It's defined for every omega belongs to real number. But if you want this calculation to be valid, I mean, to make sense, it means here when you calculate, if you have to consider two cases separately. When omega is 0 and non-zero, it means you have to calculate the value of f hat at 0 and non-zero separately. So it means this calculation makes sense or is valid when omega is non-zero. Okay, when omega is non-zero. So be very careful. So it means so far we get for f hat when omega is non-zero. Okay, when omega is non-zero, this is the formula of f hat, right? Because if omega is 0, this doesn't make sense. It means we have to calculate the value of f hat. You have to be careful. Okay, that's the case sometimes. You have to calculate the value of f hat at 0 separately. Okay, separately. So this is the value of f hat at every non-zero omega. This calculation valid for non-zero omega. Okay. So when omega is non-zero, f hat is given by this formula, the root of 2 over pi sine omega over omega. Now we have to calculate the value of f hat at 0 separately. Okay, because when you put omega 0 here, this actually is gone. Exponential 0 is 1. Okay, so be very careful. So this is f hat actually, this is f hat for every non-zero omega. Now the value of f hat when omega is 0, or simply we want to calculate f hat at 0 separately. So be very careful. F hat at 0. Okay. So again, 1 over the root of 2 pi integral from minus infinity to infinity f of t exponential minus I, look at here, minus I omega is 0 t. Okay, look at the formula here again. value of f hat at 0 separately. Okay. So this equals 1 over the root of 2 pi Okay. Again, okay, first of all, exponential minus I 0t, this means exponential 0. So this is 1, right? This is exponential 0. Exponential 0 is 1, correct or not? And look at here. So for every t, this is actually exponential 0. This becomes 0, right? Exponential 0 is 1. So this is 1 actually. Okay, this is 1. Now, similarly, if outside of this interval is 0. So this integral will be reduced to integral from -1 to 1, okay, f of t, and no harm, let me repeat this, exponential 0 dt, right, because this is 0 actually. So it means this equals 1 over the root of 2 pi. So from -1 to 1, exponential 0 is 1, and in this interval, the value of function is 1. So only left this dt, correct or not? And this is easy. What is the integral? dt is, it means t from -1 to 1, which is simply is 2. Okay, so 1 over the root of 2 pi times 2. Okay, the answer to this integral. And if you simplify it, because 2 means the square root of 2 squared, becomes this. This is the value of f hat at 0 and non-zero. So it means f hat is a case-defined function, but it's continuous. We are going to see. Okay. So you make a note first. So the value of f hat for every omega non-zero is given by this, and at 0, this is the value of f hat. So f is kind of case-defined function, but it's definitely continuous. We are going to see that f is continuous for every on R actually. Okay. So let me save this. Okay. Okay. So f hat is given by this. F hat omega is a case-defined function, right? Okay, it's given by, look at here, the root of 2 over pi sine omega over omega for every omega non-zero, and when omega is 0, what is the value of the function is given by this. Okay. So do you remember I said f may not be continuous, okay? definitely here, if you just simply, if you consider the graph of f may not be, f is not continuous, okay? Or in general, f may not be continuous, but f hat, the Fourier transform of f is definitely always continuous, including this case. So just we want to verify this. F hat is continuous. Can you tell me why? F hat is definitely continuous function. F hat from R into C, okay, is real value, but in general, complex value. It's a continuous function. Huh? Do you agree with me? This function is continuous. Look at here. For every omega non-zero, sine omega is continuous, is a quotient of two continuous function, and the denominator is not zero. So definitely it's a continuous function. Only one point we have to check, at zero. Look at here. If you want to see that the function at zero is continuous, the limit of the function at zero, okay, must be equal to the value of function at zero. The value of the function at zero is this. But can you tell me what is the limit? What is the limit? Look at here. What is the limit of f hat omega when omega approaches zero? Can you tell me what is it? We take, okay, when omega approaches zero, it means we are at the neighborhood of zero, but we do not reach zero. So it means we have to use this formula. If you take limit of this, you remember, this is very well known. You have seen this, you must have seen this many times in calculus. The limit of sine omega over omega when omega approaches zero is 1 times this. So the limit of f hat of omega when omega approaches zero equals, we have to use this formula. The root of 2 over pi sine omega over omega. Omega approaches 0. And the limit of this one is 1 times this becomes the root of 2 over pi. And what is this? This is f hat at 0. So you can see f hat at every point is continuous, non-zero and 0. Right? This means f hat is 0, it's continuous at 0. Correct or not? And also at non-zero. So you can see that f hat is a continuous function actually. So remember, you must have seen this definitely from calculus. The limit of sine omega over omega divided by omega. When omega approaches 0, this limit is 1. 1 times it becomes this. Okay, let me save this page. Okay. So this is the Fourier transform of this function. Okay, next I've provided an exercise for you. Please, okay, this is another absolutely integrable function. I leave it to you to check. Fx for every x between -1 and 1 is x, otherwise 0. Please compute the Fourier transform of f, okay? Please compute the Fourier transform of f. And then again, at the end, when you got f hat, the Fourier transform of f, it must be definitely continuous. You can observe that, you can check it. So compute the Fourier transform of f for every x between -1 and 1x, otherwise 0. Okay, next we have a theorem which is very interesting and useful for calculation of the Fourier transform of functions. So please make a note of the statement. Then we go for a break, and after break we will be back to prove it. Okay. Theorem 2.6, some properties of Fourier transform. Very interesting and useful to calculate the Fourier transform of absolutely integrable functions faster with some property. So please make a note of these properties, okay? And then we prove it after break, okay? So please make a note here. First of all, okay, suppose that f and g are two absolutely integrable functions, and omega 0 and t0 are two real numbers, fixed, and lambda is a real scalar, okay? Then Fourier transform is linear, okay? Fourier transform is linear. It means the Fourier transform of f plus lambda g, look at here, f and g are two absolutely integrable functions. It's a Banach space, so f plus lambda g is also an absolutely integrable function. So the Fourier transform of f plus lambda g equals the Fourier transform of f plus lambda, the Fourier transform of g. So the Fourier transform is linear. Actually, this is easy to see because the linearity of the Fourier transform follows from the linearity of integration. Okay. Maybe I leave it to you to check this one because it's very easy. So this is the first property. So please make a note of the statement. Then we go for a break. After break, we will be back to prove it. Okay. The second property, look at here. The second property, which is talking about the Fourier transform of the translation of f. It means like if f is an absolutely integrable function and g is a function is defined to be the translation of f. Okay, this means translation of f. G of t is defined to be f of t minus t0. T0 is a fixed number. It means g is defined to be the translation of f. Then, of course, g also is an absolutely integrable function. Okay, if you translate absolutely integrable functions, you get some absolutely integrable function, another absolutely integrable function. So the Fourier transform of g, look at here, g hat at omega equals, interesting, look at here, exponential minus I omega, let me make it bigger for you, minus I omega t0 f hat omega for every omega. So f is an absolutely integrable function. G is defined to be g of t equals f of t minus t0. This means that g is defined to be the translation of f. G is also an absolutely integrable function. So the Fourier transform of g hat at omega is given by this, equals exponential minus I omega t0 f hat omega for every omega. It's very interesting. All these properties are very useful and easy to prove, okay? So this is the second property. Please make a note. Okay, another property. F is an absolutely integrable function. If you define a function like h of t to be, look at here, exponential I omega 0 t f of t. T here is a variable. This omega 0 I, of course, constant. So if you define a function like h of t to be exponential I omega 0 t f of t, h is also an absolutely integrable function, okay? We can prove it. And the Fourier transform of h of t will be the translation of the Fourier transform of f. It means f hat. What does it mean? It means we have h hat at omega equals f hat at omega minus omega 0. It means the Fourier transform of h is the translation of the Fourier transform of f, okay? So h of t is defined to be exponential I omega 0 t f of t. Then the Fourier transform of h will be the translation of the Fourier transform of f. More precisely, it means h hat at omega e equals f hat at omega minus omega 0. For every omega. And the fourth one, or the last one in this theorem. You suppose that alpha is a positive number, positive real number. If you define u of t, a function like u of t defined to be f of t divided by alpha, t over alpha, okay? U is definitely an absolutely integrable function, okay? We can show it by if you use substitution integration. Then the Fourier transform of u hat at omega equals, look at here, alpha f hat at alpha omega for every omega, okay? So alpha is a positive number, and you define u, and if you define u of t to be f of t over alpha, okay, then the Fourier transform of u hat at omega equals alpha f hat at alpha omega for every omega in R. Okay, so you please make a note. Let's go for a break about 15 minutes, no more than 20 minutes, okay? Then we will be back to prove these properties, and then we will see what we can do more and some example. Okay, do you have any question? Is there any question? Okay, let's go for a break, about 15 minutes. Let me pause the recording here, and then we will resume it after break. Resume our recording, okay. Okay, somebody asked me to, sorry, I just see your message, to see theorem 2.6. Okay, let me finish here, I will show you again, 2.6. Okay. So this one is exponential minus I omega t0. Okay, and what is this? 1 over the root of 2 pi integral fx. It doesn't matter, use x. Exponential minus I omega x dx. What is this? This is the definition of the Fourier transform of f, right, at omega. So this equals f hat at omega. Okay, so this is this property, right? We prove it. Look at here, g hat at omega exponential minus I omega t0 f hat omega. Here, you can see g hat equals this. So all we need to do is to write down the definition of the Fourier transform of g, and g is this, and then we use substitution, then go ahead, you get this. So g hat at omega equals, it means g is defined to be, g of t is defined to be the translation of f of t minus t0. Therefore, g hat at omega, the Fourier transform of g equals exponential minus I omega t0 f hat at omega. Okay, so please you write down this one. Then somebody asked me to show the theorem 2.6. I will show you again. You write down this first. Okay, so somebody asked me to show the theorem 2.6. Okay, this is the theorem 2.6. Okay, the first one is the linearity of the Fourier transform. The Fourier transform is linear. Okay, you can see. So and then this one, the second one. And also the last one. Okay. So we already proved the first one, right? Okay. Now let's go for the, okay, first one is, I left it to you. Second one, now the third one. Okay. So the third one, okay. So now let me save this page. Okay. Now we are going to prove the third one. So, okay, the function h is defined to be this exponential I omega 0 t, t is a variable here. F of t, we want to show that this is the Fourier transform of h, which is the translation of the Fourier transform of f. Again, okay, you write down the definition of the Fourier transform of h, okay, here. So we are proving the third one. So h hat omega equals 1 over the root of 2 pi integral from minus infinity to infinity h of t exponential minus I omega t dt. Okay, and this equals 1 over the root of 2 pi exponential from minus infinity to infinity. What is the formula of h? What is the formula of h? This one. Exponential I omega 0 t f of t, right? This is our h of t, correct or not? Yes. And then this is h, and we have exponential minus I omega t dt. Okay, let's move here. This equals 1 over the root of 2 pi integral from minus infinity to infinity. Okay, look at here. You keep this f of t here. Exponential alpha plus, times exponential beta. So it means exponential alpha plus beta, right? So I can write this one exponential, okay. This plus this, right? This plus this. But do you agree with me? I can write it minus I omega minus omega 0 t dt. Okay, do you agree with me? This equals to, look at here, minus I omega t here. Minus minus omega 0 t is here. Okay, so exponential alpha times exponential beta, exponential alpha plus beta, but this alpha plus beta equals this. Correct or not? Look at here, minus I omega t minus I minus omega 0 means I omega 0 t. This is equal. Now, somebody tell me, what is this now? What is this now? Look at here, let me cover this. If we do not have this, 1 over the root of 2 pi, look at the definition of the Fourier transform of f. Look at here, the definition of the Fourier transform. 1 over the root of 2 pi integral f of t exponential minus I omega t dt. But here, what do you see? F of t exponential. It means if we do not have this, okay? If we do not have this, minus I omega t is f hat at omega. Now, in the formula, omega is replaced by omega minus omega 0. So this must be f hat at omega minus omega 0. Correct or not? Huh? Look at here. F hat at omega is integral f exponential minus I omega t. But look at here. Instead of omega, we have omega minus omega 0. This means this is the value of f hat at omega minus omega 0. Okay? So you can see we already proved the second one. Here. H hat equals f hat omega. It means it's translation of the Fourier transform of f. Little bit, we have to write this one better. Omega. This is omega, okay? Okay. Okay. Now look at here, we are going to prove the last one, that if alpha is a positive scalar, and if we define u of t to be f t over alpha, f of t over alpha, this is going to be the Fourier transform of u. U hat at omega alpha, f hat at alpha omega. Okay, let me erase here. Okay, so again, you just write down the definition of you just write down the definition of so you had at omega equals 1 over the root of 2 pi integral from minus infinity to infinity u of t u of t exponential minus I omega t dt, and this equals 1 over the root of 2 pi integral from minus infinity to infinity. Okay, what is u of t? U of t equals this, right? F of t over alpha exponential minus I omega t dt. Okay, what is next? Do you have any idea what we have to do next to get this? Huh? Do you have any idea? Okay. Again, we need to use some substitution. It means we are going to apply substitution to this integral to get what we want. So what is our substitution? What should we take? Okay. Let's take x to be t over alpha. Okay. So from here, dx will be 1 over alpha dt. Also, from this equation, we have t equals alpha x. Also, look at here. For lower and upper bound for the new integral with respect to x, because alpha is positive, okay? Alpha is positive. So when t runs or moves from minus infinity to infinity, x also moves from minus infinity to infinity. So let's move here. So we have u hat at omega equals 1 over the root of 2 pi integral from minus infinity to infinity f of, okay, t over alpha is x, okay, exponential minus I omega, and our t is alpha x, right? Alpha x, this is our t, okay? And dt equals, here dt equals alpha dx, okay? From here we can get dt, if you multiply both sides by alpha, dt equals alpha dx. So we have alpha dx, alpha dx, and this equals, okay, this alpha for this integral is a constant, right? So I can write it, this equals okay, here alpha times 1 over the root of 2 pi, the root of 2 pi integral from minus infinity to infinity f of x exponential minus I, okay, can I write this one alpha omega? These are, look at here, I omega alpha are constant. So can I write it as alpha omega? It's a product, it's commutative, the product of two number, something like that. X dx. I think we have enough space to move here. Now somebody tell me, what is this? Can you tell me what is this? What is this? Huh? Okay, this equals alpha, and somebody tell me what is this? Look at here, 1 over the root of 2 pi integral f exponential minus I, let's say omega x is f hat at omega. But look at here, omega is replaced by alpha omega. So it means if you do not have this, look at here, the integral f exponential minus I omega x dx is f hat at omega. But look at here, instead of omega, we have alpha omega. So this is the value of f hat at alpha omega, okay? So this is actually f hat at alpha omega, correct or not? So you can see we got what we want. U hat at omega equals alpha, f hat at alpha omega. So these properties are very useful to calculate the Fourier transform of the function faster without calculating directly, like similar to the property that we have for Laplace transform, right? Okay, so you make a note, then we have an example and a remark, then it is enough for today. Okay, let me save this. Okay, so we prove this, right? Okay. Next, we have an example, okay? If you remember, we already calculate the Fourier transform of this function, and we got this, right? If you remember. Before break, we calculated the Fourier transform of this function, which is given by this f hat at omega, if omega non-zero, this, and omega 0, this. Now, okay, you make a note of this. Now, we define this function, g of t, this, h, and u, okay? And then using that theorem, using the properties of Fourier transform, we want to calculate the Fourier transform of g, h, and u without calculating directly, just using the properties, okay? So you make a note of this first. Okay. So the Fourier transform of f is this. Sorry. Now, by using the theorem 2.6, it means the properties of Fourier transform. We want to calculate the Fourier transform of g of t, which is defined to be f of t minus 3, the translation of f using the property 2. And if h of t is given by exponential minus I pi t over 2 divided by 2 f of t using the property number 3. And if u of t is defined to be f of 2t, we want to calculate the Fourier transform of u. Okay, so you make a note. We are going to do this one by one by using the okay. Starting with first g, okay. Okay, here. Okay. Okay. G of t is defined to be f of uh, t minus 2, right? Okay. Here. Sorry, 3. Doesn't matter, 3. 3, okay. So do you remember by the formula, what is the Fourier transform of g hat at omega equals, you tell me. Look at the property of number 2. G is defined to be f of t minus 3. This 3 is our t0. Okay, this is our t0. This 3 is our t0, okay? So g hat at omega equals what? You remember? exponential minus I omega, okay, minus I omega T0. What is T0 here? 3. Correct or not? F hat at omega. Correct or not? Or simply means exponential minus 3I omega let me make it better. It means exponential minus 3I omega F hat at omega. Okay, but look at here, F hat is case defined, so G hat will be also case defined. Okay, so look at here, this equals okay, when omega is non-zero, and when omega is 0. Okay, look at here, when omega is non-zero, what is F hat at omega? You can see here. Is the formula, right? So this equals exponential, okay, let me write it like this. So this exponential minus 3I omega times F hat, so becomes this actually. The root of 2 over pi exponential minus 3I omega sine omega over omega. Okay, when omega is 0, look at here, when omega is 0, F hat at 0 is given by this, okay? So when omega is 0, so we have F hat at 0, exponential here also omega is 0, right? So will be F hat at 0 times exponential 0, which is 1. So it is simply equal F hat at 0, which means this. 2 over the root of pi, okay? So be very careful. Since F hat is case defined, you have to go ahead to get the formula of G hat like this case defined. When omega is non-zero, this is the value of F times this. When omega is 0, F hat at 0 times exponential here becomes 0 is 1, becomes this. And you can see again it's continuous function at every point. So this is using the second property when we have G of t is defined to be the translation of F of t minus t0. G hat equals exponential minus I omega t0. Here t0 is 3. Okay, F hat at omega. And the rest follows from the Fourier transform of F. Okay. Let's go for the second one. Okay, let me erase this. It's simple, we don't need to save it. Okay, second one. Okay, we have h of t. H of t is defined to be exponential minus I pi t over 2. Okay. F of t. Okay, now we want to find the Fourier transform of h hat at omega, which is going to be the the translation of the Fourier transform of f. It means f of omega minus omega 0, but you have to find omega 0 here, okay? Okay, look at this property number 2. H of t exponential I omega 0 t f of t. So can you tell me now here, what is our omega 0 here? This one must be in the form of like I omega 0 t. So do you agree with me? I can write this one as, look at here, exponential I, can I write this one minus pi over 2 t f of t. So what does it mean? It means our omega 0 here is, what is it? Minus pi over 2. So h hat at omega is defined to be f hat at omega minus omega 0, which is minus pi over 2. Be very careful. Minus pi over 2. So this equals f hat at omega plus pi over 2. But again, f is case defined, so we have to be careful. So we have this actually. Let me write here. Look at the formula of f. When formula of the Fourier transform of f. When omega non-zero and when omega 0. So here we have f hat at omega plus pi over 2. So it means you have to say like this. If omega plus pi over 2 is non-zero, okay, f hat at this point equals what? The root of 2 over pi sine omega plus pi over 2, correct or not? Divided by omega plus pi over 2, correct or not? And if omega plus pi over 2 is 0, what is the value of f hat? Is given by, f hat at 0 is given by the root of 2 over pi. Okay. And we can make this one like a bit better. Like let's continue here, okay, because we have a space. Usually we have to move forward, but okay, here backward here. And this equals, okay. Look at here, when you say omega plus pi over 2 is non-zero, it means simply if omega is not equal to minus pi over 2, right? Is not equal to minus pi over 2. This is the value of f. So this is given by the root of 2 over pi. Even we can make this one simpler. Do you remember if from the trigonometric function, sine omega plus pi over 2, if I'm not mistaken, equals minus cosine omega. Even you don't have to write like this. If you just leave it like that, it's still fine, but just make it maybe nicer. Minus cosine omega divided by this. Correct or not? Even if you write sine omega plus pi over 2, it's still fine, okay? And when omega equals minus pi over 2, this is the root of 2 over pi, okay? So, yes, so this means when omega is not equal to minus pi over 2, we have this, and when omega equals minus pi over 2 equals this. Again, you can check that this function is definitely continuous because it's a translation of a continuous function. Okay, and this sine omega plus pi over 2 equals minus cosine omega, okay, by the, yes, because pi, okay, goes there, cosine is, then, yes, negative, cosine is negative, negative, positive, correct, minus cosine omega, okay. So this is the answer to the second one. Okay, now the last one. Okay, let me erase this. Okay. Okay, now the last one. Okay, we have u of t equals f of 2t. Okay, we want to find the Fourier transform of u. But look at our theorem. You have to write it in this form. In the theorem, we have u of t equals f of t over alpha. Okay, it means you have to write this 2t as t over some positive number. So do you agree with me? We can write this f of 2t as f of t over 1/2. Do you agree with me? I can write it like this, huh? Let me make it a bit better here. 1/2. Correct or not? Do you agree with me? I can write it like this. T over 1/2 equals 2t. Correct or not? Okay. So now we use this property. So the Fourier transform of u omega equals, so our alpha is 1/2 here, okay, 1 over 2. So you had that omega equals alpha, which is 1/2 times f hat at, look at here, alpha omega. It means 1/2 omega. Again, f is case defined, so this equals this actually. when, look at here, f hat at omega, do you remember? If 1/2 omega is non-zero, which is equivalent to saying that, we make it better, which is equivalent to saying that omega is non-zero. What is the value of f hat at this? It's given by, okay, this 1/2 multiplied by 1/2. So 1/2, what is the value of f hat at this? It is non-zero. It's given by the root of 2 over pi sine omega over 2 divided by, so let me this one make this and not to get confused. Okay, here, when omega over 2 is not 0. So we get this, omega over 2. And when omega over 2 is 0, so what is the value of f hat? Okay, 1/2 times the value of f hat, do not forget. The values of f hat at this 0 is given by this, the root of 2 over pi. Okay, so let's continue here, make it better, simplify it. So this equals okay, look at here, 1 over 1/2 is 2, right? Simplified by this, okay, so left this becomes, okay, you may leave it like this. I mean, if you don't, but better we simplify may. That's just fine actually. But I would like to simplify it. So 1 over 1/2, yes, equals 2, okay, 2 over 2, 1. So this equals 1 over the root of, so 2 over the root of 2 over pi sine omega over 2 over omega, and this is equivalent to saying that omega is non-zero. Of course, because 1/2 is non-zero. Okay. And if omega over 2 is 0, it means if omega is 0, actually, this is equivalent to saying that omega is 0 is equal to, you can simplify. Look at here, this means the root of 2 squared, simplify by this, so you get this. 1 over the root of 2 pi. Of course, again, this is a continuous function. At non-zero, it's clear that it's continuous. At 0 also, if you take limit, the limit equals this actually. So this is the Fourier transform of u hat. Okay. So we can see using these properties, we can calculate the Fourier transforms of functions without calculating directly by properties. Quite similar to what you have seen in Laplace transform, right? In differential equation, that you define the Laplace transform, and then you have the properties of Laplace transform to calculate the Laplace transform of other functions by properties without calculating directly. Okay. So we have a remark, then it is enough for today. Okay, so we prove this, and this one, our example. Okay, now you make a note of this remark is enough. Actually, this remark is a bit longer, but we just make a note up to here just to prepare for next week. Okay. Remark 2.8. Look at here. Since we have, what is this? The space of test function in one-dimensional space, D of R, test function space, do you remember? Is a subset of CCR. Okay, this one we have seen, okay? Okay, we have the test function space is a subset of CCR, continuous function with compact support, and this is a subset of L1. About this inclusion, I explained, okay? Now, can you tell me why do we have this? Why the test function space is a subset of CCR, continuous function with compact support? Huh? Do you remember? Of course, you just remember the definition of test function. A test function is an infinitely continuously differentiable function with compact support. So if you recall the definition of a test function, it will be easy that every test function is a continuous function, compactly supported continuous function, and definitely an L1 function. So it means for every test function, we can define Fourier transform. This means from this inclusion, it follows that every test function is an absolutely integrable function. So therefore, we can define the Fourier transform for every test function as usual by the Fourier. It means the Fourier transform of, okay, phi hat omega equals 1 over the root of 2 pi integral phi of the exponential minus I omega t dt. Okay, up to here is enough. Then we can continue next week. So you make a note of this. So simply, since every continuous function, every test function is an infinitely continuously differentiable function with compact support, so definitely it's here. We have this conclusion is true. This inclusion is true, and therefore every test function will be an absolutely integrable function. So we can define the Fourier transform for every test function as usual by this formula. So you make a note of this, then it is enough for today. Little bit left for next week. So for sure next week we can finish up everything. Then we will be ready for midterm exam. And next week I'm going to mention how we are going to have our exam. Most probably I'm gonna ask everybody who is inside Thailand to come to university for the midterm exam, but people outside, they can have it online, something like that at the same time, of course, at the same time. So let me confirm what the style of the midterm exam next week. So let me stop recording, and right after class,